It is quite impossible to know about the exact events through which we humans have developed the concept of numbers. The decimal number system of real numbers we work with nowadays consists of integers, non-integers. Here our main focus is on these positive integers, which we refer to as natural numbers we use for counting. If we look back, natural numbers are the first concept of numbers created by humans long before several mathematicians and philosophers invented, designed, and modernized the real number system we see today. When our ancestors learned farming and herding, it became necessary to keep things in order while maintaining livestock and arranging bags of grains. As example, for tracking this group of animals, each of these animals required to be identified. Think about the days when there was nothing called number. To solve this problem, humans used to gather some objects like stones or sticks like this. Each of these sticks represented each of these animals, which we call one-to-one correspondence nowadays. Obviously, it was difficult for a person to track this group when number of animals was very high, and it required to gather lots of different sticks. To make this thing easier, some positional symbolic system was necessary, which could be remembered without using any physical object, stick or stone. In 19th century BC, people from Babylonian civilization came up with a solution by introducing Babylonian numerals, a sexagesimal or base 60 positional number system, which enabled a person to identify these animals through positional sequence of symbols like this. This positional number system made easier for a human mind to get an idea of how many, just by looking at this last symbol or sequence of symbols. But lots of symbols which were typically very cryptic. As example, for this number, someone had to write this sequence of symbols. For this number, I think this sequence of symbols. Not so easy, a very cryptic in fact. In 9th century BC, Roman number system was originated in ancient Rome. Numbers in this positional system were represented by sequence of letters from Latin alphabets. In this system, this number could be written through this sequence of letters and this number through this long sequence. Obviously, time-consuming and not so convenient. This kind of positional number systems were developed in several ways. The decimal number system with base 10 we see today, it took next few centuries to be introduced. Integers together with natural numbers were possible to design properly after digit 0 was invented by astronomer and mathematician Brahmagupta in the year 628. We humans became able to count objects with the help of natural numbers, and we could answer the question how many by counting number of objects gathered somewhere. Brahmagupta devised modern concepts of the fundamental arithmetic operations, addition, subtraction, multiplication and division also, which made us to do typical counting tasks with the help of arithmetic calculations. As human civilization developed, we started facing more and more complex problems to solve. Humans were interested in answering not only to how many, we were looking for the methods by which we could answer to how many ways also. This is where concept of combinatorics comes into. As a simple example, if a person has to reach from point A to point J, knowing that there are several points in between which are connected by paths, then in how many ways the person can pass through these paths to move from A to J. If we count by looking at the possible paths from A to J, these are possible paths from A to J through which the person can move from A to J. So there are 6 possible paths. Now to answer to how many ways, we can simply use multiplication rule here, which is the most fundamental principle of counting in combinatorics to find number of ways. When we take any multiple choice test, as example, there are 3 MCQs, each with 4 options. Test taker can respond to only one option of an MCQ. In how many ways the test taker can select the options for these 3 MCQs in the test. For first MCQ, test taker can select an option in 4 ways. It can be A, B, C or D. These MCQs are independent of each other. Previous selection of MCQ option does not influence the later selection of MCQ option. Hence, for each of these possible selected options in MCQ 1, test taker can select one of the 4 options in MCQ 2 in 4 ways. Then after each of these possible 2 options, test taker can select. For MCQ 3, test taker can select an option in 4 ways again. So in total, 4 to the power 3 or in 64 ways, a test taker can respond to the MCQs in the test. In all these possible arrangements, we can notice the objects which are arranged can repeat. As example, after selection of A for first MCQ, A can appear again as response to the second or third MCQ. After selection of B for first MCQ, B can come again for second or third MCQ. That's why these kind of arrangements are referred to as with repetition or with replacement arrangements. Modern combinatorics we see today this way have been possible after significant contributions given by mathematicians like Leonardo Fibonacci, Blaise Pascal in this field. Let's have a look in this urn ball experiment. These are 4 unmovable urns and 4 different colored balls. We need to find in how many ways these 4 balls can be put and arranged in these 4 urns if an urn can be occupied by only one ball. This can be an arrangement, this can be another arrangement. Total how many arrangements possible in which these balls can be put in the urns. Let's try to count the number of ways. First urn can be occupied by these 4 balls in 4 ways. In first urn, we can put the red ball or the green ball or the blue ball or the yellow ball. Let's look at the cases when we put red ball in first urn. Now second urn can be occupied by one of these rest 3 balls in 3 ways. It can be green, it can be blue, it can be yellow. So now third urn can be occupied by one of the 2 balls we are left with in 2 ways. Consider the case when we have put red in first urn, green in second urn. In this situation, we can put blue in third urn or yellow in third urn, and the fourth urn can be occupied by one ball we are left with in one way only. In this case, we can put blue in fourth urn, and in this case, we can put yellow. If we consider the case in which first urn is occupied by red and second urn is occupied by blue, rest 2 urns can be occupied by rest 2 colors in 2 ways. When we put red in first urn and yellow in second urn, rest 2 urns can be occupied by rest 2 colors in 2 ways. Similar way, when we put green in first urn, these are the possible arrangements in which 4 colors can be put in 4 urns. When we put blue in first urn, these are the possible arrangements, and when we put yellow in first urn, these are the possible arrangements. So total 24 ways of arrangements are possible in which these 4 colors can be put in 4 urns. This expression can be written as 4 factorial. Factorial notation was first introduced by French mathematician Christian Cramp in the year 1808. Notice that in each of these possible arrangements, no object, that is, no color, is repeated. Neither in this arrangement any color repeated, nor in this arrangement any color repeated. Nowhere we can see repetition of any color. That's why these arrangements are referred to as without repetition or without replacement arrangements. Here, instead of 4 urns, if we have two urns in which 2 out of 4 balls can occupy, we can have these 12 ways to arrange 2 of these 4 colors in 2 urns, which actually equals to 4p2. P stands for permutations. If we want to put 3 out of these 4 balls in 3 urns, we can have 24 ways of arrangements again. These are the possible arrangements in this case. Few more examples on arrangements and permutations. Let's assume we want to create a 5-character password in which first character can be any capital letter from English alphabet. Each of the last 4 characters can be any digit from 0 through 9 only. So in how many ways this password can be created? Let's see. First character should be any capital letter from A through Z. That means first position can be filled in 26 ways. For each letter is filled in first position, second position can be filled by any digit from 0 through 9 in 10 ways. For each of the previously arranged characters, third position can be filled in 10 ways. Each of fourth and fifth position can be filled in 10 ways. Hence, total 260,000 arrangements we can have to create this password. Now, digits in this password can repeat. As example, in this particular formation of password, 0 is repeated. That means this is actually with the replacement case we thought about. Now, what about the without replacement case? We want to see the count of arrangements in which this password can be created without repetition of any digit like this. In this case, first position can be filled in 26 ways, second position can be filled in 10 ways, third position through fifth position can be filled by these 10 digits, but we have few restrictions now. The digit we have used to fill the second position cannot be used to fill the third position. That means from 0 through 9 digits can be used to fill in third position 9 ways. 2 digits already have been used to fill in second and third position. We will be left with 8 digits to fill in fourth position 8 ways. Finally, rest 7 digits can be used to fill fifth position in 7 ways. So for without replacement case, we can have total 26 multiplied by 10p4 arrangements, that is 131,040 possible arrangements to create this password. Alex, Bella, Samuel, Tina and Nathan, these are 5 colleagues. In any office event, they are required to stand in a row to observe something. But Tina and Nathan don't want to stand together side by side. We just don't know why. So in how many ways these 5 people can stand in a row so that Tina and Nathan don't stand together side by side? Let's try to count number of possible arrangements here. At first, if we ignore the restriction for Tina and Nathan not to stay together, these are all possible arrangements in which these 5 people can stand in a row irrespective of any restriction or condition. These are 120 arrangements in total, which we get from the count of permutations of 5 people, 5 factorial. Now to find only the arrangements in which Tina and Nathan are not together here. To do so, let's find the arrangements where Tina and Nathan are together actually. Here these are. In all these arrangements, Tina and Nathan staying side by side. We will omit from count. But how many we need to omit? How to get that number? For that purpose, let's consider Tina and Nathan are a single person. And instead of 5 people, 4 people to arrange when Tina and Nathan are always together. 4p4 or 4 factorial arrangements. And in each of these arrangements, Tina and Nathan can arrange themselves in 2 ways, either this way or this way. So we need to multiply 2 here. This is the count of arrangements in which Tina and Nathan stand together. So we need to subtract this count from total number of arrangements, that is 5 factorial, which equals to 72 arrangements. These are the 72 ways of arrangements we are looking for and counted. Let's count arrangements in something different. Here is a bracelet having 4 gemstones attached in it. These gemstones are with different colors: red, green, blue and yellow. In how many ways these stones can be arranged in this bracelet during making of this bracelet? To count arrangements of objects in circular form like this, we need to keep a particular object unmovable. As example, here we can keep this red gemstone fixed. Then rest 3 gemstones can be arranged in 6 ways. Here these are. This type of arrangements are called circular permutations. Now in this case, we can notice if we alter bracelet for this arrangement, it becomes same to the previous arrangement. Similarly, these 2 arrangements are also same to respective previous arrangements. That means we actually get half of all these arrangements. In general, if there are n number of different gemstones in a bracelet, there will be n-1 factorial divided by 2 number of arrangements of the gemstones possible in the bracelet. In this kind of circular permutations, not always we can alter the thing. Suppose these are 4 people in a meeting surrounding a round table. How many seating arrangements are possible? Like before, we need to fix a person unmovable from the position. Then rest other 3 persons can be arranged in all these ways. Total 6 ways. Clockwise and respective anti-clockwise arrangements are distinct. There is no scope to alter anything here in this case. And in general, n people surrounding a round table can sit in n-1 factorial ways of sitting arrangements. So far we can notice that in all these arrangements and permutations of objects, order does matter. As example, in this Tina and Nathan standing in a row problem, these 2 standing arrangements of 5 people are distinct just because objects in these 2 arrangements are in different sequence or order, although both of these contain same objects. Now let's see the combinatorics problems when order does not matter. Here these are 5 students. In how many ways we can form a 3-member group or combination of 3 students out of these 5 students for sending the group to a debate competition. If we try to pull possible groups of 3 members from these 5 students, only these can be possible selections of 3 students. These are 10 in number. This count we can get simply by calculating 5C3, C for combinations. Here it is. In all these possible selections of groups, notice that order does not matter. As example, this group consisting Kevin, Matthew and Nancy, we can simply write this way also. It will not affect the selection of members in this group. Now if we apply few restrictions, when we select a group from these 5 students, in all possible 3-member groups, there must be 2 girls and 1 boy only. In that case, from these 3 girls, 2 girls can be selected in 3C2 ways. For each selected combination of 2 girls, from these 2 boys, 1 boy can be selected in 2C1 ways. That means total 6 3-member groups can be possible. These are the 6 possible 3-member groups in this case. Let's change this restriction to each possible 3-member group must contain at least 1 girl and at least 1 boy. That means a 3-member group can have 1 or more girls, but it must have 1 or more boys also. Let's try to count the possible cases. When a group consists of 1 girl, the only girl can be selected in 3C1 ways, and for each selection, rest 2 members in the group can be 2 boys only can be selected in 2C2 ways. Or when a group consists of 2 girls, those can be selected in 3C2 ways, rest 1 boy can be selected in 2C1 ways. So total 9 possible groups we can have, and these are the possible 3-member groups in this case. Now if we change this restriction, a group can have at most or maximum one boy. That means a 3-member group can have no boy or only one boy. So a group can have all girls in 3C3 ways, 0 boys in 2C0 ways, or 2 girls can be selected in a group in 3C2 ways with only one boy who can be selected in 2C1 ways. So total 7 possible ways to create a 3-member group in this case, and these are the possible ways to build the group. Application of combinatorics we see in several areas of set theory. As example, we have this set containing 3 members. How many partitions of this set are possible? These are the 5 partitions of this set. The number of partitions we call as Bell number and denote it by Bn with this generic recursion formula involving combination rule, and these are initial Bell numbers. So Bell number B3 for a set containing 3 members, we can get 5, as we can see these 5 partitions here. Similarly, if we take a set containing 4 elements, there are 15 partitions possible for this set, and these are the partitions. All these Bell numbers we can calculate through a triangular form called Bell triangle. Let's do quick formation of Bell triangle to see how does it work. 1, copy and paste 1, 1 plus 1 equals to 2, copy and paste 2, 1 plus 2 equals to 3, 2 plus 3 equals to 5, copy and paste 5 here, 2 plus 5 is 7, 3 plus 7 is 10, 5 plus 10 is 15, and so on. All these end numbers are the respective Bell numbers as we have seen earlier. In geometry and in graph theory, combinatorics are used for performing many counting tasks. As example, here is a 10-sided polygon called decagon. We can draw diagonal inside this way, this way, this way. Total how many diagonals can be drawn? You can pause this video for some time to think about it, and if you would like, find the number of diagonals possible in this decagon before we see the answer. It can become a tedious task if we try to count diagonals in a polygon with many sides manually. Combinatorics are helpful in these situations. Let's have a look in these points, considering these are the vertices of a 5-sided polygon, that means a pentagon. If we connect these 5 points in pairwise manner, we get these 10 edges. This count of edges is nothing but the number of possible combinations we can get when we create a group of 2 vertices out of 5 vertices, 5C2. Now to count the number of diagonals only, we need to subtract number of sides, that means subtract 5 here. So 5 diagonals can be drawn in this pentagon. Now come back to this 10-sided polygon, decagon. These are the diagonals can be drawn in this polygon. To count the diagonals only, here also we can do similar combinatorics calculations. That means 35 diagonals are possible to draw inside a decagon. In general, the number of diagonals in an n-sided polygon is nc2 minus n. We can perform counting tasks through combinatorics in programming environments. Here we will see usage of combinatorics in Julia. I am in this Julia programming environment and using this IDE VS Code Julia extension. You can find a guide link for installation of Julia and VS Code Julia extension in description below. There are many things on combinatorics we can do in Julia. We can find functions, methods for performing counting tasks in combinatorics module in Julia, which we need to install as a Julia package here. To do so, keep your computer internet connected. Then in this Julia repo, which is referred to as terminal here, write using pkg, press enter, write pkg dot add within parentheses, within double quotes, pass this module name Combinatorics. Press enter. It will download and install Combinatorics package in your computer within this Julia programming environment. Installation and pre-compilation of Julia package may take some time. After finishing installation of Combinatorics package, come to this editor to write in this Julia script using Combinatorics. Run this line to load this module in this session. Now we can call functions methods from this module. Let's start with Factorial function from Combinatorics module. Factorial 6 provides value of 6 factorial. Factorial 4 provides value of 4 factorial. If we pass another integer which is less or equal to the previous integer, as example 3, it calculates the value of 4 factorial divided by 3 factorial. Now this line, here it is. Let's see how permutations and combinations work here. Let's take a collection of objects. I am taking these 4 different characters A, B, C, D in the form of a vector, that is a one-dimensional array, array 1. Run this line. To get all the possible arrangements of all characters taken from these 4 characters in array 1, we can call Permutations function. Pass array 1, run this line. It provides an iterator. Pass it to collect function, run this line. Here these are. We get 4p4, that is 4 factorial, that is 24 arrangements without any repetition of any object in any arrangement. If we pass 3 here, collect the arrangements, run this line. It provides possible arrangements of 3 characters taken from these 4 characters in array 1. In this case also, there are 24, that is 4p3 arrangements possible. Here in this vector, we get all these arrangements in a particular sequence. To get a specific arrangement, as example, to get this 10th permutation, we can pass array 1 to nth perm function, pass 10, run this line, here it is. Now if we use nth perm with exclamation mark, run this line, it mutates array 1. Array 1 transforms itself into that 10th permutation. We can notice here in this workspace. I am taking another vector, array 2, with 6 elements. It has duplicated elements. It contains 3 A's, 2 B's, and C. Run this line. For this kind of collection containing similar or duplicate items, to get the permutations, we need to use multiset permutations function. Pass array 2, permutations containing all 6 elements. Collect the arrangements to this line. Here these are. Total 60 arrangements we get. Permutations containing 3 elements out of 6 elements in array 2 are these arrangements. Total 19 arrangements we get. Permutations of 4 elements out of 6 elements in array 2 are these arrangements. Total 38 arrangements are possible. We have seen the urn ball experiment to arrange colored balls in some urns when an urn can be occupied by one color only. This thing we can simulate here. Let's take this vector containing 5 Unicode characters, which provides a collection of 5 colors here. Assign it to a variable ball colors. Run this line. You can find all these lines of code in the source code link given in description below. Permutations of 4 out of 5 ball colors are these arrangements. Permutations of 3 out of 5 ball colors are these arrangements. To find possible groups or combinations of elements, we can use combinations function. Pass array1, collect the groups, run this line. It provides all combinations of all possible sizes from the elements in array1. Similar combinations we can get if we use powerset function. But powerset function includes this null combination and empty collection also. To get the possible combinations of any specific size, as example, to get all combinations of size 3, we can pass integer 3 with array1 to combinations function. Collect the combinations, run this line, we get 4 combinations, 4c3. If we pass 2 here, collect the combinations, we get 6 combinations, 4c2. When we do sampling from any population, as a simple example, suppose we have this population, a collection of 4 objects. We can pull a sample of size 3 in these ways. These are nothing but all possible combinations of 3 objects taken out from 4 objects. That means these are 4c3, that is 4 combinations here. In each of these possible samples, elements are unique. There is no repetition of object we see. This is the sampling without replacement. These possible samples we already have found here in Julia. Now many times we need to create samples which can hold elements with repetition also, like this. These are all possible samples of size 3 when we do sampling with replacement from this population of size 4. We get 20 possible samples or combinations here. We can get all these possible samples while doing sampling with replacement here in Julia using with replacement combinations function. Pass this array1. We want to pull possible samples of size 3 from array1. Collect the samples, run this line. Here these are. As we have seen before, to find possible permutations of elements in array2 with duplicate elements, we can find possible combinations with specific size also from a collection with duplicate elements, as example array2 here. For that purpose, we need to call multiset combinations function. Pass array2 with duplicate elements. Let's get combinations of size 3 from array2. Pass this iterator to collect function, run this line. Here these are. We get 6 possible combinations. Pass 4 here. Now we get 5 possible combinations. We can find functions, methods in Combinatorics module in Julia to get partitions of many kinds. As example, integer partitions function. Let's pass an integer 5. It's an iterator now. If we pass it to collect function, run this line, it provides all these ways of partitions for 5. We can simply use partitions function also to get all these partitions in this order. Now if we pass an integer less or equal to 5 as example 3, collect the partitions, run this line, it provides all possible partitions of size 3. Partitions function has several methods we can notice. Let me take this vector array1 we have worked with before. If we do partitions of this collection of 4 elements array 1, we can get 4 non-empty subsets in form of respective vectors in one way. Here it is. We can get 3 non-empty subsets in 6 ways. Here these are. We can get 2 non-empty subsets in 7 ways. Here these are. And 1 non-empty subset in one way. Here it is. 1, 6, 7, 1. All these numbers are respective Stirling number of second kind following this summation rule involving calculations of combinations. Sum of all these Stirling numbers of second kind is actually the Bell number, which is the count of all these possible partitions together we saw. From Combinatorics module in Julia, we can find this multi-exponents function. It actually returns the exponents in any multinomial expansion. As example, if we pass 2, 2 to this function, pass this iterator to collect function from this line, it provides this collection of exponents in binomial expansion of power 2 in the form of respective vectors. Similarly, exponents in binomial expansion of power 3, exponents in trinomial expansion of power 2. Here these are. Exponents in trinomial expansion of power 3. We can go on. Thank you for watching. For any query, please write in comment section below. If you would like to support, simply click on thumbs up button. Share this video to someone who may get help from it. You can subscribe to this channel as well. See you in any other video. Goodbye and have a good day.